Okay, I apologize ahead of time. I get really excited about this section. Um, I'll try to focus on answering the homework questions, but I'm probably going to go on a couple conceptual tangents. Not tangents, because it's really involved, but yeah, this is really great stuff. So let's start by looking at number 2. So every year we have 1,500 students. There's a lot of word problems in these sections. There's a lot of applications. There's a lot of words. What I'd highly recommend doing right off the bat is just write down the key things. Do you see 1,500 students? Just write that down somewhere. Okay, maybe that's our population. Maybe that's our sample. Who knows? Take the intro stats course at a large university. This year on the final exam, the scores are distributed with a median of 74. So the exam has a median of 74, a mean of 70, standard deviation of 10. There are no students who scored above 100, but a few are below 20. None above 100, a few below 20. All right, and it's first off, it's asking us, is this symmetric, right skewed or left skewed? Couple ways of doing this. Remember the difference between these. Symmetric, it doesn't have to be normal. It could, be some other shape, but symmetric just means symmetric, right? Is it reflected around some middle? Right skewed means the tail is on the right. Someone's skiing. They're skiing downhill. Which way are they going? They're skiing to the right. You don't want to ski on the left, you're going to die. All right? Or left skewed would be the opposite. The tail is on the left. Remember, left and right doesn't talk about the hump. It talks about the tail. This is the tail. Is the tail on the left or the right? Okay. So, which one is this? A couple ways of doing this. Remember, when we talked about skewed, we said the mean is affected by outliers. The mean is affected by these few guys. This one, the mean should be bigger. Mean is really affected by outliers. This one, the mean should be smaller. So that's one way of approaching this question. Our mean is smaller than the median. It needs to be skewed to the left. Another way of doing this is just looking at the actual data. The center is at 74. But there's none above 100. So 26 above, there's nothing. But there is stuff that's 50 below. The spread is much bigger on the left. Skewed to the left. Right? If this is our median, the median's not actually the peak, but this is our median, right? There's only a couple things bigger, up to 100, but there's a lot of things smaller. Few ways of answering that question. Would you expect most students to have scored above or below 70 points? Well, we know that half of the students scored above 74 and half scored below 74. So if 74 is the half, then above 70 is going to be more than half. Right? If you think of, half are on the left of 74, half are to the right of 74. But the question is asking us about, what about 70? What's bigger than 70? Well, more of them are going to be bigger than 70. It's a way to visualize it. All right. Just double checking in my head. Yeah, great. What's the probability that the average score for a random sample of 40 students is above 75? Now we're really getting into sampling distributions. We're taking a sample. There's 1,500 students who took this class. Population is 1,500. Okay, that we know that now. Our sample is just the 40 students that we're looking at. 40 students is that sample. So every time we take a sample, maybe we're doing a simple random sample, maybe a systematic sample, maybe some other kind of sample. Every time we take a sample of this population, we're going to get, on average, different students with different exam scores. The sample's a random variable. It's a number that we don't know yet that's going to be different every time we try it. That's what sampling distributions is all about. How does this random average, this average of 40 exam scores, how does that change every time we take a sample? We're only going to take one, but we don't know what that value is going to be because it's random. Once we take it, we'll have an answer. So what we know about sampling distributions of means is that if we can use the central limit theorem, then, and we'll check that. I'm pulling up the notes right now so I can show it to you. Then we know something about the standard deviation and the mean. So do we have all of these? Is our sample random? We can assume that. Is it independent? Yeah, we're going to get independence because we're drawing without replacement. We're drawing without replacement is bad for independence, but we have the 10% condition. Remember that 10% condition says that if your sample is less than 10% of the population, then we get independence. So 40 is less than 10% of 1,500, we get independence. Sample size condition, usually 25 or 35 is big enough. We talked about all those in the notes. So this is bigger than 25 or 35. It is skewed. If it were normal, we wouldn't really need this 25, 35 requirement, but because it's skewed, we will. So, okay, yeah, we can use the central limit theorem here. So, check off all the boxes. We know that this mean, this sample mean, is a random variable, and it's normally distributed with mean mu, the population mean, and standard deviation sigma, population standard deviation, over the square root of n. We have all of these things. What's the population mean? Well, this is the population, and this is the mean. So that's our population mean. This is our population standard deviation. So you just plug things in, and we're good to go. Oh, and this is our n. So we go over here and say, all right, every time we take a sample, x bar is our sample, it's going to be a random number. Let's call that capital X bar for its random variable. The mean we said was 70. Standard deviation is sigma over n, which is 10 over 40. Sorry, 10 over the square root of 40. What is that approximately equal to? About 1.5811. And GeoGebra, or sorry, MyOpenMath is sometimes a little finicky. Let's add extra decimal places just to be safe. 3883. Oh, we'll go off the page. All right, and that's our sampling distribution. So now what are we being asked? What's the probability that this average score is above 75? What's the probability that the average is above 75? Gosh, my greater than signs look like sevens. Average is greater than 75. Well, this is a normally distributed random variable. How do we in this class, there's a lot of other ways in other classes, but how do we in this class find probabilities for normal random variables? We use GeoGebra. So what's the mean of this normal random variable? 70. What's the standard deviation? 1.5811. $38.83. And we want to know what's the probability that we're bigger than 75. Not very big. 0.08%. Pretty unlikely. Right? Because this is 3 standard deviations above the mean. Approximately, right? More than 3 standard deviations above the mean. This is our standard deviation. This is our mean. We're many standard deviations above the mean. It's going to be pretty rare. Now, a single student getting an exam score above 75 is very common, but a random sample of 40 students, their average is going to be really close to 70 because of our sample size, basically. The sample size makes that standard deviation smaller. All right. We got to move on. But that's some conceptual review for this stuff. Oh, I should put our answer 0.008 like this. Make sure I'm not leading y'all astray. Hey, we got them all right. Great. All right. I have office hours soon. I will do number 5. The manager of a retail store is concerned that his suppliers have been giving him laptop computers with lower than average quality. His research shows that replacement time for the model laptops are normally distributed with a mean and standard deviation as follows. So normally, the laptop age is normally distributed with mean 4, standard deviation 0.4. Pretty small standard deviation. He then randomly selects records on 48 laptops sold in the past and finds the mean replacement time was 3.8 years. X bar 3.8. Why am I using X bar? Because he selected 48 random ones and found their average. Selecting some random subset of the population, getting the average, that's sample mean. Assuming the laptop replacement times have a mean of standard deviation like was claimed, find the probability that 48 randomly selected laptops will have a mean replacement of this bad or worse. It's supposed to be 4. Find the probability that we get something under 4 like this or worse. This is a lead into hypothesis testing, Unit 8. Sneaking it in there. It's a good question, though. So find the probability that X bar is less than 33.8. Well, we could go through the, for time purposes, I don't want to go through the central limit theorem again in this video, but we could do so. It's important to do. We know that the mean of the sampling distribution for X bar is going to be the same as the mean of the parent population. And the standard deviation is going to be sigma divided by the square root of n, and n is 48. So 0.4 divided by the square root of 48. Our standard deviation is 0.05773. 503. You don't need this many for the quiz. Usually 4 significant figures is going to be good for the quiz, but always best to play it safe with my open math, I think. So this is a normal random variable. Just calculate a probability for a normal random variable. We use GeoGebra. Normal random variable here has a mean of 4 and a standard deviation of whatever number we just said. I think you can copy paste. Let's see. Great. You can copy paste. What's a probability that's 3.8 or less? That's greater than, Jason. Nice try. Oh, I didn't mess it up. It was GeoGebra. It's just not clicking over. Great. What's the probability that's less than 3.8? Not very much. About 0.03%. So this is what Unit 8 hypothesis testing is going to be all about. They claimed it has a mean and standard deviation of 4 years and 0.4 years. But we just took a sample of 48 and got a mean replacement of 3.8 years, which is smaller. But maybe we just got unlucky. So we found the probability of that happening. If this claim is correct, this is the probability that we could have gotten this unlucky or worse. That's really, really uncommon. It's so rare. I don't think we just got unlucky. I think the suppliers are giving us crap. Okay? Yes, they are giving us bad quality laptops. This is so unlikely to have occurred by chance alone. Where do we draw the line in the sand? What's the difference between unlikely and likely? We talk about that in Unit 8. A good rule of thumb is 5%, but it really depends on the context. Your margin of error is going to be a lot bigger for selling laptops than it will be for medicine, for example. All right, one more question. Let's do number 8. A food marketing institute found that 42% of households spend more than $125 a week on groceries. Let's write that down. 42% spend at least $125 on groceries. Try to translate this into some math. Assume the population proportion, okay, we're talking about proportions now. Sampling distribution of means is related but different from sampling distribution of proportions. The population proportion, we always use lowercase p for population proportion, we're assuming is 0.42. And we took a simple random sample, sampling methods, Unit 1. Simple random sample of 199 households. Our sample size is 199. And that's selected from the population. What's the probability that the sample proportion of households spending more than $125 is between 0.25 and 0.47? Find the probability that the sample proportion, that the sample proportion is between 0.47 and 0.25. Well, if we know the distribution of p hat, then we can calculate this probability. If we know how this random variable behaves. Every time we take a sample of 199 people here, we're going to get a different sample proportion because it depends on who we ask. It's a simple random sample. They're going to be asking random people, right? So, can we use the central limit theorem for proportions? We need independence. Are these again, this mentions the 10% condition right here. And we can assume the 10% condition because we're only looking at 199 people, but we're talking about households in the United States, presumably. Yeah, 199 is less than 10% of those households. Good. Do we have randomization? It's a simple random sample. Great. Success failure condition. You should have at least 10 successes and 10 failures in your data. Well, how many do we expect? We have a sample size of 199. We expect 42% of those to be successes. Yeah, that's going to be bigger than 10. You can calculate it out. We have 199 and we have a 58% chance of failure. Yeah, that's going to be more than 10 too. This is the success failure condition up here. You can check that these are both more than 10. Again, we got a bit of a time crunch today, so I'm not going to do it now. We know this is normally distributed with this mean of p and this standard deviation for PQ over n. I just got too excited talking about probability and sampling distributions and statistics. Let me know if you have more questions about this stuff. All right, so let's fill in the blank. P hat, we just need a probability for p hat. We know its distribution, we can get there. The mean of this normal distribution is 0.42. The standard deviation, we're going to have to calculate that. What's the square root of PQ over n? Well, that's the square root of 0.42 times 0.58 all over n, our sample size of 199. Type that into a calculator. If I can find my calculator. Square root, oh dear, sorry. Square root of 0.42 times 0.58 divided by 199. About, we'll copy and paste that, 0.03499. We'll copy and paste that into GeoGebra so we can find this probability. It's a normal distribution. We know the mean. We know the standard deviation. That's the standard deviation. Let's make sure it copied correctly. Yep, there it is. And the mean, what was the mean again? 0.42. What's the probability that we're between? So we're going to click this icon. 0.25 and 0.47. Were those the numbers? Yeah, they were. We can visually see it up here and get the answer down there. 0.25, really unlikely. 0.47, that's closer to the mean. It's going to be this shaded area. Area of a normal curve is its probability. And that's going to be about 92.35%. Pretty likely. All right, 0.9235 is going to be our answer. That's how you can approach these sampling distribution of proportions questions. Let me know if you have more questions. It's perfectly 10 o'clock. It's time to answer your guys' questions in office hours. Have a good one. Bye-bye.